Hello. In this podcast, we're going to be learning how to do advanced analysis of position time graphs. Specifically, we're going to look at calculating displacement and distance, average velocity versus average speed, and we're going to learn how to predict elapsed time and position. First, let's review some key terms. We have elapsed time, and that's the time between two events, calculated as delta t, which is the symbol for elapsed time, is equal to the time of the final event minus the time of the initial event. So for instance, let's say we started at 0 seconds and the object finished moving at 10 seconds. Our elapsed time would be 10 seconds minus 0 seconds for a total elapsed time of 10 seconds. Displacement is an object's change in position between two events calculated as delta x, the symbol for displacement, is equal to the position at the final time minus the position at the initial time. For example, the object starts at position 5 meters and finishes at position 2 meters. The displacement, delta x, is equal to 2 meters minus 5 meters is equal to negative 3 meters. Yes, displacement can be negative, and that just means that the object moved in the negative direction instead of the positive direction. Distance, or path length, is the total length of the path an object traveled between two events. For example, if an object moved 5 meters to the right and then 2 meters to the left, its path length was 7 meters. That's the 5 meters it traveled to the right plus the 2 meters it traveled to the left. With distance or path length, the numbers will always be positive. Velocity is the rate at which an object's position changes, and that's given by lowercase v is equal to displacement divided by elapsed time, and we get that by taking the final position minus the initial position and dividing that quantity by the final time minus the initial time. So for example, in our problem up here on displacement, at time 0 the object was at 5 meters, and 10 seconds later, at time equals 10 seconds, it was at position 2 meters. So our displacement would be negative 3 meters, our elapsed time would be 10 seconds, and when we do that division, we wind up with a velocity of negative 0.3 meters per second. Velocities can be negative too. That just means the object's moving in the negative direction. Finally, let's look at speed, and that's the rate at which an object's path length or distance changes. So speed is equal to the path length divided by the elapsed time. So if we take our example up here on distance or path length, we saw that the object moved 5 meters to the right, then 2 meters to the left for a total of 7 meters. So the path length was 7 meters, and it did that in a total of 10 seconds, our elapsed time, and if we do that division, we find that the speed is 0.7 meters per second. Notice that the speed will always be a positive number, so speed is associated with distance or path length, and velocity is associated with displacement. Let's move on now and take a look at displacement versus path length and how we calculate them from a position time graph. So in our first example here, we want to calculate the displacement from time equals 0 seconds to time equals 10 seconds. Well, first, its displacement is the final position minus the initial position. So we have to go to 10 seconds on the graph and find the position, and that's 12 meters. So we have 12 meters subtracted from the initial position. So we have to go to 0 seconds, and notice the position is 0 meters. So that gives us a displacement of 12 meters. Now let's look at the path length for the same time interval, 0 seconds to 10 seconds. So we started at 0, and at 10 seconds we had moved up to a total of 12 meters. So here we didn't travel any distance at all, we were standing still, and here we increased by 12 meters. So again, the distance is 12 meters minus 0 meters, or a total of 12 meters traveled. Now, displacement and path length won't always be the same. So let's take a look at this example. We're going to look at the displacement from time equals 8 seconds to time equals 16 seconds. Well, first we want to find the final position, so that's at time equals 16 seconds. So we go up here and read the graph, and we find that that's at position 6 meters. Then we go to the initial time, which is 8 seconds, and we go up and we read the position there, and it's 8 seconds. So the displacement is 6 meters minus 8 meters, or negative 2 meters. Now, for path length, we want to study each segment. Notice the graph or the object changes direction. So we can think of this as two segments. From 8 seconds to 10 seconds is a straight line, and from 10 seconds to 6 seconds is a different straight line. So in our first segment, from 8 seconds to 10 seconds, we started at position 8 and we moved up to position 12. Well, that's a total distance of 4 meters. So we put that down into our equation. And now we have to add to that the distance traveled in the second segment. So at 10 seconds, we were at 12 meters, and 6 seconds later, at 16 seconds, we were at 6 meters. So we went from 12 meters to 6 meters. Now remember, we're looking at distance, and there are no negative distances. There can be negative displacements, but not negative distances. So in the second line segment, the object traveled a total of 6 meters. So we add the distance traveled in those two line segments, and the total distance traveled was 10 meters. Notice the change in position or displacement was negative 2 meters, which would be 2 meters to the left or 2 meters down, depending on whether we're moving horizontally or vertically. But the total path length or distance was 10 meters. So when you have a change in direction, you'll find that displacement and path length are different. And displacement can never be longer than path length, but path length will be longer than displacement when you have a change in direction. When you have no change in direction, for instance from 0 seconds to 10 seconds, we didn't change direction, the path length and the distance will be the same. Next, let's look at average velocity versus average speed. So we had measured the displacement from 0 seconds to 10 seconds, and now we just need to remember that velocity is the displacement divided by the elapsed time. So that's 12 meters divided by 10 seconds, and that's 1.2 meters per second. The average speed for that time segment is also 1.2 meters per second. Because our path length was 12 meters and our elapsed time was 10 seconds, so we do the division and we get 1.2 meters per second. And remember, when we do not change directions, which from 0 seconds to 10 seconds we did not change direction, the displacement and path length will be the same. Well, if displacement and path length are the same, then velocity and speed will be the same. Let's take a look at an example where they're different. So here in the segment from 8 seconds to 16 seconds, we are changing directions. We start going in the positive direction and then wind up going in the negative direction. So our velocity is the change in displacement, which is 6 meters minus 8 meters, or negative 2 meters, and the elapsed time is 16 seconds minus 8 seconds, which is a total of 8 seconds. So when we do the division, our average velocity is negative 0.25 meters per second. And that just means we're moving in the negative direction at 0.25 meters per second. Now let's take a look at the average speed. Well, the average speed is the path length, and notice our path length from 8 seconds to 16 seconds was 4 meters plus 6 meters for a total of 10 meters path length, and we're dividing it by an elapsed time of 8 seconds, and we have a velocity, we have an average speed of 1.25 meters per second. So again, when you have a change in direction, you'll find that the velocity, the average velocity, will be different than the average speed. And again, the average velocity can never be greater than the average speed, but the average speed will be greater than the average velocity when we change directions. Let's move on and look at how we can predict the position and time of an object or two objects. Here we have a graph. We have object A. It starts at position 8 at time 0 and moves to the right or the positive direction. And object B at time 0 starts at the origin, position 0, and it also moves to the right. Now we can tell that the slope of object B is greater than the slope of object A, so that tells us right now that B is going faster than A. However, A has a head start, an 8-meter head start. Well, a question we might get is, what are the positions of A and B at 15 seconds? Well, our graph only goes to 10 seconds, so we can't read where they'll be from the graph, but we can use the graph to figure out or calculate our predicted time and position. So first, we want to see how far A is going to be. And we start with A's starting position, which was 8 meters. And then, if we notice the slope of this line, in 4 seconds, the object A went from 8 meters to 14 meters. Well, that's a total of 6 meters displacement in 4 seconds. Well, that's a slope of 1.5 meters per second, or its velocity. So if we know it's moving 1.5 meters every second, and it's moving for 15 seconds, if we multiply those two, it'll tell us that the object has moved 22.5 meters. But that's not the position it'll be at, because it had a head start and started at 8 meters, not at 0 meters. So the position will be 8 meters plus 22.5 meters, or position 30.5 meters. Let's do the same thing for object B. Now object B starts at 0 meters, so we put our starting position down there. And if we look at the slope of this line, we can see that in 4 seconds it went from 0 meters up to a position of 8 meters. So 8 meters displacement divided by an elapsed time of 4 seconds tells us that it's moving at a velocity of 2 meters per second. That means every second it's going to move another 2 meters. Well, if it travels for 15 seconds, then in those 15 seconds it's going to move 2 meters per second times 15 seconds, or a total of 30 meters. And since it started at 0, its position will be 30 meters. Another type of problem we could be asked is, at what times do A and B reach the 40-meter position? So let's take a look at this. So for A, we want to find how long, or the elapsed time, it takes to get to the 40-meter position. Well, it started at the 8-meter position. So to go from the 8-meter position to the 40-meter position, it only needs to travel 32 meters. So that's the 40 meters minus the 8 meters. And we know that it covers 1.5 meters every second. That's the velocity. So if we divide this velocity into the change in position, the 32 meters, we'll find that it takes 21.3 seconds for object A to get from the 8-meter mark to the 40-meter mark, which is up here off the graph. Now let's do the same thing for object B. The amount of time it takes to get to 40 meters, well, it's starting at 0, so it needs to travel 40 meters in order to get to the 40-meter position. And we know that it's moving 2 meters every second. That's its velocity. So we divide the velocity into the total displacement, and we find that it takes 20 seconds for object B to reach the 40-meter mark. We can also be asked how much faster B is moving than A. So we know by looking at the slopes that B is moving faster than A because the slope of B's position time graph is steeper than A's position time graph. But we can also calculate how much faster. So how much faster would be the difference in velocity, delta V, and it would be B's velocity minus A's velocity. This expression is the velocity of B, and we got that from the graph because we saw at 10 seconds the position of object B was 20 meters, and at 0 seconds the position was 0 meters. So the change in position, 20 meters, divided by the change in time, 10 seconds, gives us the velocity. And likewise, this expression is the velocity for object A. And we got this from the graph. At 10 seconds, the position was 23 meters, and at 0 seconds, the position was 8 meters. So this is the change in position or displacement divided by the elapsed time or change in time. So when we do the division here, we get 2 meters per second, and when we do this division, we get 1.5 meters per second. So we subtract the two velocities, and we find out that object B is moving half a meter per second faster than object A. Let's look at one more thing we can predict. At what time will object B catch up to object A? So we know that B is moving faster than A, but A has an 8-meter head start. So how much time will it take for B to erase that 8-meter head start? Well, let's take a look. So here we have the head start that A has, so that's 8 meters minus 0 meters. So A has an 8-meter head start. Now we know the difference in velocity is 2 meters per second minus 1.5 meters per second. Or we know that B is going half a meter per second faster than A. That means every second B is going to get half a meter closer. Since B has to close an 8-meter gap, and it closes it at a rate of half a meter every second, if we divide 8 meters by half a meter per second, it'll tell us how long it'll take object B to catch up to object A, and that is 16 seconds. Now graphically we would see that by the two lines intersecting, but of course since 16 seconds is not on this graph, we don't see the lines intersecting. But had we been able to extend this graph out to 16 seconds, these two lines would intersect, showing that the two objects were at the same position, meaning that B caught up to A. Well, this ends our podcast on the advanced analysis of position time graphs. I hope you found this helpful, and have a good day.